The following is a conversation with Geetanjali Sethi, Associate Professor teaching at St. Stephen College in Delhi. I hope you enjoyed the conversation. This is Back to the Stone Age. Geetanjali, what is energy, first of all? Because sometimes when I am looking around myself, I believe it is very easy for me to point out sort of the other content of the universe, which is matter. I can see matter everywhere. It's very easy for me to detect. But maybe the concept of energy sometimes might be not as intuitive as the concept of matter. So, what is energy?
So energy is a very broad term, even in physics, but particularly when you talk about energy in cosmology, it includes everything, including the energy equivalent of mass. Because if you know from Einstein's equations, Einstein's mass energy equivalence, E is equal to mc square. Anything that's massive has mass, has some inherent energy, right? So even for that matter, so if you think of matter, matter can be thought of as some source of energy. So when we talk about energy density or energy in context of cosmology, it includes everything that's present in the universe that contributes to its its existence, its energy, in the sense like mass, radiation, or even components like dark matter and dark energy, which we cannot see. So all this comprises what is called the energy budget of the universe. So even mass, anything that has ability or ability to do or to or to contribute to growth, dynamics of the motion, dynamics of the universe is what constitutes or what contributes to energy of the universe. So that's how you look at it. So dynamics of the universe itself is because of the energy content of the universe.
Okay, so energy is more a concept related to motion and dynamics.
Yes.
Okay.
Dynamics.
You mentioned dark matter and dark energy. Now, we know it is pretty common, it is pretty widely known that our best physical theory, which is the standard model, explains only 5% of the content of the universe, which, if stated like this, might not sound a great achievement, but it, of course it is. So you mentioned that about dark matter and dark energy.
Yes.
How do we know that such things exist, and what are in principle, or what do we believe these two things are?
Okay, so just like when we started discussing about energy, I told you it is what is responsible for the dynamics of the universe. So when we look at the dynamics of the universe, in the sense, like in early 1920s, astronomers, like very famous astronomers like Hubble, people, the cosmologists, they discovered, what they found was that the galaxies inside in the universe are receding away from each other. That is, they are actually moving away from each other, and the farther they're moving away at a faster rate, right? So what does this mean is that universe is expanding, and expanding at an accelerated rate. That is, the rate of expansion is increasing with time. To explain this, if you use the Einstein's equations and you arrive at the dynamical equations of the expanding universe, you see that you require much more than what you can actually see in terms of visible matter or radiation present inside in the universe, right? So that's how you come to even this number like 5%, right? Where do you come to this number from? 5% is by looking at the expansion rate of the universe itself. So when you measure this expansion rate, you require much more than what is measurable in terms of radiation or what you can see, what you call as visible matter, normal matter, right? And that's what gives rise to ideas like dark matter, dark energy, things that you can't see, that don't interact with normal radiation, and hence are not visible to you. And since they don't have interaction, they don't undergo interactions like electromagnetic interaction, so they are not you cannot detect them by measuring their charge or any other way. So they don't interact with your normal matter. Right? So that's why that's where this whole idea of something extra other than what you can measure with your eyes or see or measure with your existing detectors, that idea comes from.
And when you think about dark matter and dark energy, how do you picture? Well, the main topic of discussion today is dark energy, but for both of them, how do you picture them in your mind?
Well, to picture anything, you always need to have a physical model. That's what you normally, visualizations are always governed or assisted by making some physical measurements. So, since here there have been no physical measurements, nobody has observed any kind of interaction. So, I mean, it's very difficult to say how I can visualize it because you can't imagine it as a particle. You can't imagine it like anything physical that exists around you that you know. So a visualization of anything like dark matter or dark energy is difficult. What you can visualize it as or what you can see it as is something that comes through indirect interactions. For example, when you look at, there's a very famous bullet cluster. That's where one very strong evidence of existence of dark matter comes from, is where you observe so in the bullet cluster, it's like two galaxies are colliding and you look at their collision and there are shock waves which are generated, right? So when you look at those shock waves and you study the dynamics and you try to visualize those shock waves, you see that you require something that's not visible to you, that there is something that exists there but it is not visible, but it interacts gravitationally, right? So that's how people kind of make indirect observations or indirect measurements of, in this case it's dark matter, right? Or when you make measurements of what you call as rotation curves of galaxies, right? That is, you look at the motion of stars inside the galaxy and you map that as a function of their distance from the center of the galaxy. That's what you call as the rotation curve. When you look at the radial, you look at the velocity of stars going around the center of the galaxy. You observe that if you plot those rotation curves, you see that the rotation curve flattens, right? But if you consider normal orbital motion, you will see that velocity goes as if you look at velocity, it should decrease as you go farther away from the center of the galaxy, if it's only simple ordinary matter. So there are these indirect evidences which help you understand their existence. It's difficult to visualize them because you don't know what their nature is, what their true nature is. And you don't know what kind of physical interactions they follow.
Okay, do you believe or not do you believe it? How does it sound to you? Because to me it sounds pretty ironic that we humans could infer through indirect effects the most amount of content of the universe, and only approximately 5% of it we can actually see it. It seems that sort of either the universe is way more complicated for us to understand, or yeah, actually only that. It seems that the universe is way more complicated.
Yeah, no, I agree with you. It's actually something which has been really keeping cosmologists, astrophysicists involved, because it's really astonishing that we've spent so many years, we've been studying this area, but we only know 5% of what our universe consists of, right? And we've spent so much money, so many satellites, so many missions, so many space stations are in place. But yes, I agree. I mean, it's true that we really know very little about uh, what really exists in our universe, right? And yeah, So maybe with new missions, we might have a better idea soon. Let's hope soon about, and our knowledge becomes much better than this 5%.
That's true, yeah. So what is then dark energy? Has referred to the expansion of the universe that you were mentioning before, because sometimes a very rough description that people give about this dark energy, they just say, oh, well, it is simply the expansion of the universe, or the energy driving the expansion of the universe. Is it like that?
It is, yes, indeed. It's not like a very simple explanation, but yes, that's what is the observation, that the universe is expanding and expanding at an accelerated rate. Now, there's no, these things are now quite well established. This idea that universe is indeed expanding and expanding at an accelerated rate. There are almost all observations, different parameters that we measure in cosmology support this idea. So this idea is now kind of more or less kind of agreed upon, that the universe is indeed expanding at an accelerated rate. And there is something that is responsible for this expansion, because if you just go by what you can see, right, anything that interacts gravitationally will only be responsible for an infall, because gravity by nature is an attractive force, right? So it will only pull things inside, but things are moving apart and at an accelerated rate. Then there is something, something has to have this negative pressure so as to overcome the attractive force of gravity, right? So that's the nature of that is what is not known. That's what people have been speculating, different models people have been exploring, is what, yes, people call as dark energy.
Okay. When I was reading into dark energy and trying to deepen my understanding of it for this conversation, I bumped into the concept, which was sort of not counterintuitive, but let's say pretty weird to me, where they say that empty space, we know through quantum mechanics that it's not empty, it's not always empty. It can possess its own energy, and while the universe expands, while space stretches out, then more of this empty space sort of gets created that has more of this energy, which drives more of this expansion rate. Is that a correct description of what is going on?
I did not get what you just meant. I mean, what you just said about more pockets being created.
Yeah, more empty space being created, space being stretched out by the expansion of the universe.
By the expansion of the universe.
Yeah.
Right. Yeah. So yes, if you think of what really, so this is what is called the 0-point energy, or the vacuum energy density, the energy density possessed by the vacuum, right? So if you imagine, if you look at a simple harmonic oscillator, if you think of a simple harmonic oscillator and you think of it classically in the sense not using quantum mechanics, simple classical physics, then classically, the lowest energy state of a harmonic oscillator would be the oscillator at rest, hence no kinetic energy, and would be at the bottom of the potential well, so zero potential energy. Hence, you can have zero energy as the minimum energy state. But if you look at this quantum mechanically, the scales, the initial scales, the early time when the universe was not of the size what it is now, at those scales, if you look at quantum mechanics, I mean, the uncertainty principle doesn't allow both position and momentum to be measured simultaneously with great accuracy, right? So there is some kind of uncertainty. And this is what you see as, hence the 0 point energy measured is more than zero. It's greater than zero. So quantum mechanically, 0 point energy is a finite energy. It's finite, right? But if you look at this number only in terms of quantum mechanics, then it's arbitrary. You can give it any, you can denote it by any number, right? It could be anything. It could be anything in the sense you can even set it to be equal to, it's your 0 point energy scale. So basically in quantum mechanics, you measure only differences, right? You don't measure absolute energies, you measure differences. So if you look at quantum mechanics alone, you can treat this 0 point energy as some zero of your measurement scale. But when you include gravity, when you have gravity and you look at quantum mechanics, then this is not true. Then this energy is not zero, right? So this is what is the energy of the vacuum, right? And the vacuum energy. And this, the fluctuations in this energy, this vacuum energy, because of the uncertainty principle, is what is seen as the, what a part of dark energy, what you call as the cosmological constant, right? What people think was the initial, and this particular very popular, currently one of the most popular model, the lambda CDM model, is this is what is known as the cosmological constant. That's the value of the dark energy at the very initial epoch. And its cosmological constant and the lambda CDM model assumes that this value remains same throughout the evolution of the universe, right? So this is what you see as, or what you are referring to as the energy of the vacuum, and is what is responsible for the expansion of the universe.
Okay, you mentioned the Heisenberg's uncertainty principle, and I would like to ask you about that. Do you believe that this uncertainty principle works sort of as only as a limitation for human beings in our understanding and comprehension and measurement of the physical processes, or is it sort of a universal limit of understanding? Meaning, is it something more, let's say, tailored for humans, or it is an intrinsic property of the universe?
It is an intrinsic property of any quantum system, in the sense it's intrinsic property of any system. And quantum mechanics is a well-established theory. It's been well tested, well established, and the results that you get from quantum mechanics in atomic theory, structures of atoms, and the behavior of atoms are very well understood, fairly well understood. Right? So uncertainty principle, or uncertainty in the measurement, is an inherent characteristic. It's an inherent property of quantum systems.
Okay. What do you believe is the weirdest or the most mysterious thing about quantum mechanics?
Well, I think quantum mechanics is less weird. It's quite well understood, in the sense people do really understand. And as you said, it's a limitation, or it's only for humans in terms of measurements. So however you improve your measurement, however you improve your technique, measuring technique, you will always have a certain minimum uncertainty in your measurement, right? So I feel quantum mechanics is less weird. It's weird. It's more difficult than weird. It's difficult again because you can't visualize it. So wherever you lack visualization, it becomes difficult to understand, to accept things which you can't visualize. So I think the weird thing, or the limitation about quantum mechanics, is because it's difficult to visualize. I mean, I would not say that it is weird.
Do you have mysterious or beautiful thing about quantum mechanics that when you studied it as a student, you were particularly struck by?
Well, what I really like about quantum mechanics is that, see, one thing about quantum mechanics is you can't solve it on pen and paper. Almost anything that's a real physical system cannot be solved on pen and paper, right? It has to be solved computationally, right? So what I really enjoyed when I first learned quantum mechanics and I started studying was that you could visualize things. You could if you use computers, if you use programming, if you do computational work, then it's the results of quantum mechanics really begin to show their true picture, in the sense modeling, looking at hydrogen atom, measuring energies of atoms, the transitions of atoms and things like that, right? This is something that it's not possible for me to go and do in the lab, right? But I can do it computationally, right? So that's what I really enjoyed. I really found interesting about learning quantum mechanics as a student at that point of time. Yeah. And I
Okay.
love teaching it as well.
Okay. Which courses do you teach?
I'm teaching, I've taught, last semester I taught quantum mechanics, I taught astronomy, astrophysics.
Okay.
I do computational labs for quantum mechanics.
Okay. Now, Geetanjali, maybe more back to the dark energy topic. When I was reading into it, I saw, and as you probably mentioned before, that dark energy has constant energy density. But my sort of puzzlement, my doubt was, well, but if space is expanding, right? We know that space is expanding, and we know that the dark energy in it shouldn't it get diluted in the expanding universe? So how can dark energy have constant energy density?
In fact, what you are saying about dilution is exactly what my past few years of research has been on, looking at models of dark energy. So when you talk of constant energy density, so what I said is what you call as the cosmological constant, right? It's just one kind of model, cosmological model, and that's not the only one, right? This is, as I said, it's one of the most popular cosmological models, where the contribution to dark energy comes from the vacuum fluctuations only. That's what you call as cosmological constant, and its value remains constant over the whole dynamical history of the universe. But this is what exactly leads to two very important, or rather two very big issues, two very big unsolved problems in cosmology related to the lambda CDM model or the cosmological constant, is the fine tuning problem and the cosmological constant model, where, as you also said, it's really astonishing that how can something to that great accuracy can have the same value over 13 billion years, right? That's the fine tuning problem. That is the value needs, that's the cosmological constant problem, that the value of the cosmological constant remains same, and the fact that it is so finely tuned to a particular value. Why? Because if you even slightly change the value of the cosmological constant, everything falls apart, right? It is cannot be explained, right? So it has to have that very, very exact value. That's the biggest, these two are two very big problems with the cosmological constant model, and has led to further studies in alternative dark energy models. Like one kind of such models is what I have been working on for last few years, is a dark energy model where the dark energy is treated like a cosmic fluid, treated like a fluid, has properties of a fluid, but has an equation of state that varies. So what you call as fading, yes, that's true. As the universe expands, the behavior of the dark energy, literally, or its contribution to the energy density, the total energy budget of the universe changes. Right? So yes, you're very right. It's actually strange, and that's what cosmologists are trying to look at, is that the value of the cosmological constant being so finely tuned to a particular value. But yes, there are other models where you have models of dark energy where this doesn't happen, where you don't have a single cosmological constant. You have contribution coming from other exotic kind of material. Exotic because, again, yes, we don't know what the origin of these uh, exotic things is, but we try to model equations of state mathematically and see if they can explain the dynamics of the universe, right? And I've been working on one such model, and I've been getting very good results uh, in terms of explaining the observed behavior of the dynamics of the universe. Right? And it's not a cosmological constant model.
Okay. Now I'd like to delve a little bit into these models indeed. And the first one that I would like to ask you about is probably one of the first cosmological models, I believe, which is the Friedmann-Lemaitre-Robertson-Walker model. It's a very long name. What is
Yes.
what does this where does this model come from? What are the assumptions of this model, and what are the sort of implications for the universe that it describes?
Yeah. So FLRW model, that's what you can call it as, um, is the basic model, the most general model of the universe. It is based on two assumptions. That is, the universe. It's a model that is explained by what is called the FLRW metric. So when you solve the Einstein's equations with the energy density, with the contribution coming to the energy density from various components, and you arrive at the dynamical equations describing the dynamics of your universe by using what is called the FLRW metric that describes your space-time. The behavior, the nature of your space-time is what you call as the FLRW metric, and it's based on two assumptions, and that is that the universe is homogeneous and isotropic. That is, if I look at any part of the universe, on large scales, on very large scales, the universe is more or less, if I cut any patch of the universe and I measure the content, I look at the content of the universe, it's homogeneous, and there is no vantage point. That is, wherever I stand, there is no favorable location in my universe. It looks the same from anywhere, right? That's what I call as isotropic. So it's based on these two assumptions. If you include into the Einstein's equations on the mass energy tensor side, contribution from the cosmological constant, then the model that you get is what you call as the lambda CDM model. That's the most popular, because if you look at the original FLRW model without the cosmological constant, it cannot explain the accelerated expansion of the universe. So you have to add this term in the energy budget while solving the Einstein's equations, the cosmological constant, and that's when your equations, the dynamical equations, can explain the accelerated expansion. And then your FLRW model leads to what is known as the lambda CDM model.
Okay, where
So
lambda
that's
is
lambda means the cosmological constant. You denote it by a lambda, so you call it as the lambda CDM model.
which is
CDM
the
stands for
fine-tuned.
whole dark matter. Yeah.
Okay.
Yes, to fine tune. Yeah.
Okay. And you don't believe in this fine-tuning?
Well, I've been working, as I said, it's difficult to say whether I believe it or not, because the model that I've been working on, and I've used various cosmological observations to test. It's just one of dark energy models, and it does explain, and it does give me it fits in quite well uh, with the observations, right? Uh, yeah, and the fine tuning and there are other places also where the lambda CDM model is falling, is what is now recently people are now talking about is the Hubble tension, right? That is I mean, if you look at Hubble parameter is again, it's a measure of Hubble parameter is a measure of expansion of the universe, right? Rate of expansion of the universe. The present value of that is what is called as the Hubble parameter. The present expansion rate is measured in terms of what is called the Hubble parameter. Now, Hubble parameter is a parameter that is measured using different observations in cosmology, right? And when you use the lambda CDM model to estimate the value of Hubble parameter, you get very different values from two very well measured or well established cosmological tests: the cosmic microwave background radiation and the supernova. And the value differs at what we in cosmology, I mean, in data science, otherwise is also called the 5 sigma measurement level, right? So it's really, really different. You get very different values for the Hubble parameter from these two tests in cosmology. Like if you measure the Hubble constant from CMBR, you get a value of around 67 kilometers per second per megaparsec. On the other hand, from supernovae, you get that value to be around 73, right? And that difference is very large. It's quite large, right? So that's again where the lambda CDM model is falling apart. So I feel that it's worth visiting alternate models.
Do you believe there are other, let's say, worse and worthy of noticing problems with these models?
Oh, yes. Different models do have different limitations. I would not say that there is anything that's like a best fit as of now in cosmology, something that explains everything. But like I said, I've been working on this exotic fluid model, and recently my last paper that I published 2 months back, the agreement in the value of Hubble parameter. Though I have not done the CMBR test, but I've done other local and distant tests like fast radio bursts and supernovae, and even using the gravitational waves and GRBs. And I've got a good agreement in the value of H naught. And currently we are working on the CMBR data in this model. Let's see what kind of results we get. But yes, for all other models, I've got quite consistent values of H naught.
Okay.
And I've seen that in various other dark energy models as well.
Okay, what are other dark energy model or cosmological model? I read about models like Quintessence and modified gravity. What are they?
So quintessence are like, again, for example, when you talk about lambda CDM model, it's like you have a constant contribution coming to the dark energy, which remains same over epochs during the dynamics of the universe. Whereas there are other models where you have these varying equation of states, or you get varying contributions from dark energy. So behavior of dark energy, I can just to give you an example of the model that I've been working on, what you call as the Chaplygin gas model. When we look at the dynamics of Chaplygin gas in the cosmological model, in and look at the dynamics of the universe, you see that initially the contribution from the dark energy or from the variable Chaplygin gas, it behaves like normal matter at very early epochs. On the other hand, at very later epochs, it behaves like the cosmological constant. That is, it has a constant equation of state. So what are these various dark energy models? Are actually mathematically, what you understand by them is that they have different equations of states. Equation of state is how pressure relates to the energy density. So basically, how the energy content of the universe is responsible for the dynamics in terms of the pressure exerted by this energy content, right? So that mathematical relation is what you call as equation of state. And that's what describes these. So different equation of states, different mathematical models of these equations of states is what describes these different dark energy models, right? So how pressure relates to the energy density is what a different dark energy model would be. So quintessence is one such category where you have a varying contribution coming from the energy density of the dark energy. On the other hand, as you said, so if you think of how do we arrive at dynamical equations of universe is by solving the Einstein's equations, right? Einstein's equations has two sides. One side is the energy content, that is matter, radiation, what all contributes to energy content of the universe. And the other side is the geometry of the universe, right? That is the what is your geometry, whether it's a curved space-time, flat space-time, expanding, what kind of geometry your universe has, right? So when you look at different kinds of contributions coming to this energy density side of your Einstein's equations, these corresponds to different dark energy models. That is where you look at different exotic material, different things contributing to total energy density, and hence the dynamics of the universe changes is what you call as the dark energy models. On the other hand, people have also been working at not changing this side of the Einstein's equations, not changing the energy budget, not adding these exotic dark energies, but changing the geometry side of the Einstein's equations is what are known as the modified gravity, right? Where you change the structure of the space-time. So keeping the energy budget or the energy content of the universe to be matter and radiation, something that you observe, but changing the basic structure of the space-time. So these are two different categories of cosmological models. So when you change the energy, the structure of the material or the things that contribute to energy is what are different dark energy models, right? There you can have cosmological constant, you can have these quintessence, you can have varying equation of state models, right? But you keep the gravity to be ordinary, normal gravity that you, gravitational models that you think of. On the other hand, you can keep the left hand, this energy budget side the same, but change the basic structure of the space-time. Those are what are called the modified gravity models.
You've been working.
People are trying. Yeah.
Sorry.
No. So people are trying to look at modified gravity models as well.
You have been working on, you just mentioned the variable Chaplygin gas model,
Yes.
which I've never heard of. I kind of knew about lambda CDM, NFL, RW model. And when I read into it and I read your part of your last paper, you indeed describe this model with the main character to be this cosmic fluid. What is this cosmic fluid? And again, probably this is a ill-posed question, but how, when you work on the Chaplygin gas model, how do you picture in your mind, or at least how do you imagine this cosmic fluid to be?
So, cosmic fluid or cosmological fluid is like this exotic material that we kind of use to model. Now, as an example, in case of variable Chaplygin gas models, the models that I've been working on, you have this single fluid. So fluid is like its dynamics is governed by fluid equations from fluid dynamics. This single exotic fluid explains or to get unifies the dark matter and the dark energy. So you don't have dark matter and dark energy existing separately, but it kind of behaves like matter at an early epoch, and then like dark energy, which is the dominant component now. So it dominates in form of dark energy today. So this is the cosmic fluid when we talk about in case of variable Chaplygin gas model. Right? So Chaplygin gas models, this general class initial model was actually known as the Chaplygin gas model, which was a much simpler model where you had pressure as inversely proportional to the energy density of this fluid. So the equation of state describing this exotic fluid, this exotic cosmic fluid, was that pressure of this fluid is inversely proportional to the energy density and negative of it. So since it's inversely proportional to energy density, it increases as energy density decreases. In the sense, as you said, the universe expands, energy density, that is mass per unit, energy per unit volume, decreases, the pressure increases because it's inversely proportional. And negative, in the sense, it kinds of pushes it. It's responsible for pushing it away. So that's that's how you mathematically describe this cosmic fluid. This model has grown over years. Equation of state has been modified, keeping in the initial idea, that is pressure being inversely proportional to density with a negative sign, various functions of density, not just 1 by rho, but various functions have been explored. So one such mathematical model with a slightly varied in equation of state as compared to initial is what you call as the variable Chaplygin gas model.
And what are the assumptions of this model?
So the assumption of this model, it's based on the fact that the energy density is a function of epoch. It goes as a power law in epoch, that is, it goes as an inverse power law in epoch, and the pressure is inversely proportional to this energy density with a negative of it. That's the assumption, that the energy density is a function of epoch in the sense function of time scales, which are also measured in terms of what you call as the scale factor, that is the measurement of size of the universe at different ages, and is inversely proportional to, the pressure is inversely proportional to it. Right? So that's the assumption, that the energy density changes with time. That's the assumption. This exotic fluid that behaves in this way.
What would you say are the main differences of this model from other models as lambda CDM or FL RW? Would you say that this assumption is probably the main difference?
Yeah, this assumption is the main difference. Like in FLRW original model, there's no lambda C, there's no dark energy. If you add to it a constant dark energy is what you call as the lambda CDM, which remains same. The contribution remains same over epochs. Whereas a model like variable Chaplygin gas has a varying equation of state, and contribution to energy density from dark energy varies over time.
How does this model?
Yeah, its behavior changes over time. Sorry, yeah.
Okay. How does this model emerge in the past?
So in the past, when we do not require dark energy to explain the expansion of the universe, it behaves, the variable Chaplygin gas behaves like a normal matter. Its equation of state is similar to ordinary matter. And since its equation of state evolves, it evolves in such a way that today it behaves like a cosmological constant. That is, the energy density contribution is like a cosmological constant energy density in today's time. So that's how it varies.
If you had to bet, if you were forced to bet all your money or a huge amount of money on any of these dark energy models, which one would it be?
Oh,
You cannot abstain from the bet. You have to.
that's dangerous. I mean, the way things are changing in cosmology, the way things are developing, if you look at last 15 years, the both precision and accuracy in the cosmological measurements has changed, grown drastically, right? I would refrain from betting.
Yeah.
Because you don't know things, the way things are changing, right? The way the data is coming from
The observations. Yeah.
the observations are happening, it's just amazing, amazing. In fact, few days back I happened to come across one of these videos which talked about how people claim that they have solved the Hubble tension problem. That is, they have with the lambda CDM model, and they've kind of, the observations now show, the observations are now such that they explain the Hubble tension, right? Though it was just a, I mean, when I was watching it, it was just a conference paper. It's not peer reviewed or published yet. So I don't know how much trust one can have. But I mean, the way things are changing in cosmology overnight, it's extremely difficult and very tricky.
But
Yeah, but
okay.
I'll continue to work on the variable Chaplygin gas for some more time.
Okay. But now I have to insist. Let us say you now are forced to bet, and then you get frozen, and then you will be unfrozen only when the truth, if it will ever be known to humans, will be revealed. What would you bet your money on? What would you
I would
say?
actually, I would actually look at something different from something that has a variable equation of state, and not going for a cosmological constant, right? Because as I said, it's very difficult to really explain how, and also the way the value has been fixed, right? It's very difficult to accept the way that has happened, right? So I would still go for varying equation of states and try to explore, right? And wait for particle physicists to come up with some exotic particles that can explain this kind of behavior.
So I can see, I can understand that you are firmly against these fine-tuning problems, these fine-tuning explanations for the cosmological constant. But now I would like to ask you, don't you believe that in nature and in our universe, there have been so many, probably uncountable many other cases where fine-tuning, not in physical theories, but in sort of cosmological values, meaning our constant of natures that made life possible, have been the case. One example, I mean, we can find so many examples of where if we would vary one constant of just a very small fraction, then probably uh, galaxies could not form, life could not emerge. So how do you sort of deal with these other fine-tuning, naturally occurring fine-tuning problems?
But yes, I agree. I mean, so all this is that's exactly what is very intriguing, is that you have all these things so finely tuned, right? But I'm really worried, in the sense people have been trying to work on trying to find for such a long time, right? And it's something that is not directly measurable, right? If you talk about other, I mean, there are various parameters. I agree. If you look at the ratio of, for example, gravitational force to the electromagnetic force and gravitational constant or Planck's constant, all these are constants which are, the values are so finely tuned. But the observations kind of try to support, in the sense, as I said, quantum mechanics is a very well understood theory as of now, right? I mean, the observations and everything support the way it explains things. It's very, it really fits into place, right? On the other hand, various cosmological observations themselves are not being, for example, a better measured parameter like Hubble parameter measured from observations, the value of the Hubble parameter. So these things are not supporting, are really kind of not really supporting the cosmological constant value, right? And as I said, yes, if observations are able to give more confidence, bring in more confidence, so it's more like confidence in the values rather than supporting the fact that these are, so there's confidence in the values, other parameters, though there are people, I mean, people in physics always look at or are still studying, as you said, that there are so many constants which are so finely tuned, right? People are still studying that how can all these parameters be so finely tuned, right? If you change the value of Planck's constant slightly, right, the behavior or the quantum systems, the way the things happen around us will completely fall apart, right? But then observations do support that value of the Planck's constant. That similar kind of confidence I still feel is missing in case of cosmological constant. It appears to be have been put there by hand, and the value being, how the value is being determined. So it's a tricky question, right? I mean, it's a tricky thing to say that, yeah, true. I mean, everything for that matter, that's what has been bothering physicists for, and still bothering. People are still studying how these values of different constants are so finely tuned. It's true. It's true for all physical constants. The gravitational constant, the Planck's constant. Yeah. So I mean, if something like quantum gravity would have, people would have been able to uh, put together, combine quantum mechanics and gravity and the quantum gravity theory, then things would have been, we would have been more confident, right, in something like cosmological constant. Right? That's what is missing. That's what is one of the biggest problems in physics.
What about the framework that the variable Chaplygin gas model tries to build? Does it include also dark matter, or is it only a dark energy model?
It's a model that combines, there's no separate thing as dark matter or dark energy. There's this one exotic cosmic fluid which behaves like dark matter or matter in initial epochs of the universe and behaves like dark energy because it has a varying equation of state. So you don't have separately like dark matter and dark energy, but this something that behaves like dark matter at early epochs and dark energy at the present epoch. So these are called unified models.
Do you believe that it is easier to come up with a unified model trying to unite dark energy and dark matter, or is it more reasonable to try explain them separately?
Well, as I said, there's no win-win. There's no choice, or there's no win-win situation in either case, right? People, we don't know what kind of exotic matter can have a behavior like variable Chaplygin gas. Right? These are theoretical models. These are mathematical models. There's no particle or there's nothing that we know of which will have a behavior like this. Right? So I saying that whether a model with dark matter and dark energy separately or both, the only thing that one can say is that definitely the two kinds of things do exist in our universe. There is something that behaves like matter, that interacts, that has gravitational effect, but you can't see it because it doesn't interact with photons or electromagnetic radiation, and yet contributes to what contributes to gravity, or what contributes to mass, or behaves like matter in the sense of gravitational interaction. And then there is something like dark energy, which completely behaves in the opposite way, counteracts dark energy, counteracts your gravity. So you really require both these things. How you model them is completely a theoretical idea.
And theoretically speaking, what are the features of the universes as explained by the different dark energy models that we discussed today? For example, lambda CDM, or for example, the variable Chaplygin gas.
So the future, I would say, is now completely dependent on observations, on the results that we get from these surveys. So the dark energy survey, or the other surveys that are now going to map deeper parts of the universe, right? So that's what is now going to really lead to what is the true nature, right? So we're completely dependent on, you can keep coming up with theoretical models, right, mathematically, but you don't know what kind of material will behave like this. So now you are completely, I mean, now I feel that cosmology has now become an observational science. It's completely observational, highly dependent on what we observe.
Do you believe that there still is room for geniuses a la Albert Einstein to come up with some new crazy idea about our universe and revolutionize our understanding, or observational cosmology has just taken over and it is useless to spend time on trying to elaborate finer and more accurate models theoretically?
No, it's not useless. It's not useless. I would not say. I mean, as I said, when I say that I'm completely dependent on observations, I believe things can actually go completely. I mean, they can just take any turn, any turn. We're still, that way, cosmology, we are living in a very interesting era in cosmology, right? Still don't know a lot, but I feel that next 10, 15 years are going to be very, very interesting.
What do you believe is the most interesting or fascinating or most puzzling thing about the cosmos?
If somehow dark matter is some way dark matter is detected, I really look forward to, people have been for now quite some time building these dark matter detectors, right? That's going to be really fascinating if we can observe any such kind of interaction in coming years.
You previously said that you have taught astronomy and astrophysics at university, right?
Yeah, at undergraduate level, yes.
At undergraduate level, yeah. So especially in astrophysics, but as well as in astronomy or cosmology, I would say most of the time, I guess, at least very, very often, you are exposed to gargantuan numbers, gigantic numbers regarding cosmic scales, talking about billions and billions of light years across from one part of the universe to the other.
Right.
Now, whenever I read about either in a book or I am watching some videos and I hear people talking about these numbers, just putting forward these numbers, it seems like as if these numbers are kind of taken not trivially, but they are not truly thought of. Do these huge numbers make sense in your head? Do you actually realize, or do you actually conceptualize in your mind somehow how actually big compared to you and your physical experience is cosmic scales of billions of light years across?
Uh, I completely understand. This is something that I always tell my students when I start teaching, when I go for my first lecture, is to give them an idea about, is to give them a feel about these numbers. I mean, the scales at which we are talking about. So we're not talking about the smallest scale that we talk about in astronomy or astrophysics is our solar system, right? Yeah. Earth-Sun distance, right? So, which is one astronomical unit, which is huge as compared to anything that you can, or even for that matter, Earth-Moon distance. It's huge as, and I agree that these are numbers which are difficult to absorb. Not only difficult to absorb, but are also limitations in cosmology. If you look at time scales, uh, which are more relevant in cosmology rather than talking about distance scales. I mean, you really look at phenomena. The phenomena happen over billions of years, right? So, yes, it is very difficult to accept because you cannot, for example, in the lab, right? How do you establish uh, or you make a measurement is by making repeated measurements of anything. Suppose I want to measure time period of a pendulum, right? How will I do that? How do I know how good my measurement is? Is what I will do is I will repeat the measurement 100 times, 1,000 times, 10,000 times, and I will make a measurement of time period. And then that is what is going to give me confidence in my measurement. On the other hand, in cosmology, what are my testing grounds? My testing grounds are supernova explosions. They don't happen every day. They happen over billions of years, and I cannot wait for the next one to happen. It may not happen in my lifetime. Forget about my lifetime. It may not happen again in the lifetime of my own solar system, right? So not only distance scales, time scales, though both are interrelated, are very, very difficult to understand in cosmology or astronomy, astrophysics, and are indeed limitations of the science, right? Of this field, because you can't wait to test your observation by repeating that or waiting for that event to happen again during your lifetime, right? So yes, I completely agree on that ground that and yes, I feel that is the limitation. It's really scales, but we've really progressed in terms of observations and measurements, right? For example, our own galaxy, which is megaparsec scales, we mapped it so well, uh, quite well, in that sense. So we are trying to overcome limitation in terms of distance measurements, right? Measuring things over large distances, right? Yeah, but definitely that way it's as difficult to accept as quantum mechanics. They're two extreme situations. Both the scales are very difficult, unimaginable, because you can't visualize, right? But here, the beauty in astronomy, astrophysics, and cosmology is You take your telescope, go out, and you can at least see things and get a feel that they're really far. Uh, 'Cause you don't see things changing so drastically. You see that things in the sky remain almost same over months and years. It's because they're so far away, right? That you can't see them moving, you can't see them changing, uh, even when your Earth is rotating at a time of 24 hours, right? Uh, so I think observations is what gives you feel about these distances and time scales.
We have been talking about dark energy as basically the driving force of the expansion of the universe. Do you believe that the universe will keep on expanding forever?
Uh, well, I would not say it's a belief. I would say that's what my observations are currently telling. That universe is the model that fits the observations best is indeed an expanding universe.
And when you are thinking about a universe that is expanding forever, what does a never-ending universe um, sound, or how does it sound in your head? An infinite universe in size.
Uh, as you said, it's already you can already imagine it as if you compare it with the length scales that you are so used to looking at, right? The most distant galaxies are almost like an infinite distance, right? So far away, right? So
But infinity, however, is way larger than um, even the furthest galaxies that we see in the observable universe, because infinity is by definition never limitless, never ending. So sometimes when I think about cosmic scales, which according to my experience are of course uh, gigantic, if I do try to actually compare them to what infinity in my finite mind looks like, where well these cosmic scales actually don't seem very big, because if I have to imagine a never-ending universe, then probably 94, 93 billion light years in diameter of our observable universe doesn't seem too big.
see, right now what we can observe is 13.6 billions. That's what may be. I mean, that's what we can do right now. We don't know if there is anything beyond that already. I mean, we have, that's what we kind of look at or observe. By my observations tell us, though if you look at the recent observations, few recent observations made by JWST, uh, the James Webb telescope, they have kind of mapped galaxies that appear to be actually much older than the size of the universe that we currently measure it to be, right? So how good even the current measurement of the size of the universe is a question, right? Is something that we are still exploring, that we are still looking at uh, with observations, right? So if you really try to explain those observations, they seem to be almost double uh, in age as compared to what we currently think of the age of the universe to be, right? So infinite or limitless universe would only, what I can visualize it as is that as you keep exploring, you keep going deep, farther and farther, deeper and deeper into the universe, is that you keep finding these older and older galaxies. So, I mean, well, I don't know if we will ever, if we'll ever be able to live. Definitely, it's not us. When I say able to live, uh, whether human civilization would actually survive to see this limitless or infinite uh, universe to be, right? I mean, our dynamical scales are much smaller than the dynamical scales of the universe, right? It's very difficult to say, or to for me to say how I visualize as infinite, or for me infinite or ever growing universe would mean that it follows mathematically the dynamical equation that currently it is expanding at a accelerated rate, and it continues to do that.
So you do not believe in a big crunch, as
Well,
many theories hypothesize.
it's as I said, it's very difficult to say that I believe in something or not, right? It's more, as I said, is supported by observations. uh, what I believe is in what I observe, right? And what my observations are telling me, right? So currently my observations, I mean, there are people, who believe in big crunch or are working with those kinds of theories. So believing may not be really the right way to say. I would say that observations kind of support currently an expanding universe.
Do you think that artificial intelligence could win a Nobel Prize in the 21st century?
Well, the way it is growing is definitely at a rate faster than
The
the
expansion of the
observation,
universe.
the expansion of the universe. Yes, true. So uh, that's up to us to see uh, how do we compare it. But yes, I mean, the powerful, it's extremely powerful. The way one can analyze data, huge amount of data that we are getting, I really see, at least what I really see is the utility. What I really look forward to is utilizing it in the positive sense of analyzing huge amount of data in a very shorter duration of time. So that would probably, at least, if not, if AI doesn't win whether it wins a Nobel Prize or not, but it will definitely, can definitely be used to come at results or analyze results much faster than what has happened in the past. Is to use it for good research.
Could it be the case that as we progress our understanding of the working of the universe, um, well, it has always been the case that as we progressed our understanding, we just found more and more questions to pose ourselves. Um, could it be that the never-ending process of questioning the reality around ourselves is actually encoded in the development of our finite and humanoid brain?
Mm.
The incapacity of fully grasping the truth.
Well, again, I mean, it's like, what do you mean by truth? What do you really, I mean, it's a very, I feel it's more of a philosophical idea, that when you say truth or something,
The full
again,
explanation of the working of every physical process surrounding human beings.
but then we will definitely have, as I said, as you only said about AI, and I think that will always assist the limited capacity uh, of the human brain, right? Isn't it? I mean, I don't know. I mean, even even the way we've been thinking, our thought process, our thinking skills, our line of thought has also evolved um, over years, right? And again, the evolution, the way we think, the way we analyze, has come from what we've been observing, right? What we've been getting, what we've been learning more and more. So I think that capacity of learning, that capacity of analyzing, mm, has been growing over the years, in the sense that we now know, that we now already know a lot more than what we knew in the past, right? And that has helped us. And so if you talk about limited capacity of our brain, I think that limit is also, isn't that limit also evolving? Isn't that limit also changing with time? In the sense, there's no well defined limit in that sense. We learn more as we observe more, right? And when we learn more, as when we observe more, we analyze more, right? So I feel we are also driven, our thinking capacity, our learning capacity is also driven by, it's not just us, it's also driven by what happens around us, what we see, what we are able to do, what we are able to get from our surroundings, right? So if we get more information, right, I feel that that limit increases, of thinking or analyzing increases. If I get more information, I'm able to think better, think more, analyze more. And I feel we'll keep getting more information, right? And we are getting more. So uh, I don't know. I mean, that's as I said, it's more of a philosophical idea, difficult to answer
Well,
in that sense.
we can always do, and we can always say, as Joseph Louis Joseph Louis Lagrange would often be saying, I know only one thing is, and that is that I do not know.
Yes, that's true. That's actually true. We really know that we do not know. That's, and I think that's a good, that's even a, I feel that even that's good. That's a good approach to also think of it, because that's what helps you grow, right? And think more.
Thank you for this conversation, Geetanjali.
Thank you. Thank you so much. It was wonderful talking to you. You seem to be really pursuing your, um, I would say, interest beyond what you study, what you really learn, your passion. And you're already at a very good level, or a good level of understanding when it comes to astrophysics or cosmology. Good luck. I think you'll enjoy doing it.
Thank you so much.
Thank you. It was nice talking to you.
This was a conversation with Geetanjali Sethi. I hope you have enjoyed it. This was Back to the Stone Age.